Welcome back to my Advent of Code 2015 series. Today I'm doing something different. Instead of just showing my solution process without commentary, I'm going to present my solution to this problem. I got stuck on the problem for a while. I got interrupted when I was solving it and I wasn't able to solve it in one session. The second part of the problem is probably one of the most difficult problems in all of the 2015 Advent of Code. The first part, however, is kind of simple. So the problem is that we have a string of characters, for example, ho ho ho, and then we are tasked with finding how many unique strings we can get from this by using a list of text replacement rules. And the list looks like this. We can replace an H with an HO, or an H with a OH, or an O with HH. So for example, in this string we could have replaced the O here with HH, resulting in HHH, and then the following ho ho. Okay, so how many different unique strings can we get by applying these replacements wherever possible? My solution to this first part is that I first parse the rules into a list that looks like this. So here we have a list of tuples. Every tuple contains the left-hand side of the rule, which is one token, in this case one character, and the right-hand side that we will replace the left-hand side with. And then I have a set, because we want to know the number of unique strings we can get by applying replacements. Then we have the starting string x. Now we need to iterate over every character position in the starting string and see if we can apply one of the rules to that position. And we do that by first looping over every character position in the input string, then looping over the rules, and here in the loop I split them up into the left side and the right side. So we need to check if the string starting at the current position in the input string, if that starts with the left side of our rule, then we can build a result string by taking the text up to this current position and appending the replacement text, the right side of the rule. Then after that we concatenate the rest of the string, excluding the current position and also the whole length of the string we are matching. So if the left side has length greater than 1, we need to make sure that we do not include any of the left side in the result. And then the answer to the question is just the number of unique elements in the set. So we get that with len s. The second part of the day 19 problem was much more difficult. And now the question is kind of flipped. Instead of having this input string and then finding strings we can produce by applying rules to it, we are tasked with starting from a constant string e. And then the question is, how can we produce the target string, which is the input is now a target string that we want to produce by applying all available rules to this starting string e. And the question is, how many replacements is the minimum to reach the target string from starting with e. So here are how the rules can look, and the left-hand side of the rule doesn't have to be only one character. It can be, for example, CA blah blah blah. So I split these into tokens. So in the problem description, these are actually elements. So O is oxygen, H hydrogen, but I don't care about that. I just care about how I can match these. So I call these tokens. So Rn is one single token, and AR is another token. Okay, so I split the first I parsed the rules, and then I split the left hand side and the right hand side into tokens. The left hand side is always one single token, and the right hand side is at least 2 tokens. And my first idea for solving this problem is that I could use breadth first search. So starting with E, then we can produce a set of follow-up strings. By taking every possible replacement and applying to the string, we get some following states. And this is very natural to solve with breadth first search, where you have kind of a search tree where at every position in the search tree you have some follow-up states, and you add them to a queue, and then you work through the queue until you find a solution. However, breadth first search only really works if you have either a shallow search tree or a very narrow but deep search tree. So if this search tree is both wide and deep, then the search takes way too long, and that was the case for this problem. I tried implementing breadth first search, but it was obvious that it was way too slow. And then these rules, they kind of reminded me of parser grammars. So I started thinking about using a parser generator. If I could encode these rules as a parsing grammar and then use a parser generator to generate the parser, then the solution would just be to count the number of times I match each rule from the parsing grammar. However, I tried that with the parser generator Bison, but the grammar is ambiguous, and I didn't want to spend more time trying to get that to work with, for example, a generalized parser. So then I thought about using a recursive descent parsing. And recursive descent could work, however, there is a problem with left recursion that we have here. So I thought, what if I use a limited recursion depth? And I will explain now my idea with that. So left recursion occurs in parsing grammar where you have some rule that can match a token with a new string that starts with the same token. So for example, in this case, replacing H by HCA, then we have the same token on the left side. So then we can see that if we start from H, then we can obtain HCA, and then we can replace H again, and we get HCACA. We can replace H again, and then we get this thing, and it keeps growing and growing and growing, and it keeps going infinitely. So if we add a recursion limit instead, then we can prevent this infinite recursion problem. But the recursion limit requires tuning. If we have too big limit, then we spend too much time recursing down into dead ends. If the limit is too low, then we might not find the solution, even if there exists a solution, because we haven't traversed far enough down in the search tree to find it. So sorry for the wall of text, but this is pseudocode, or this is the code of my solution, but simplified a bit for presentation. So I have a core parse function here, and this will return either the no match constant, which is a tuple containing -1, where the first element of this tuple indicates the number of replacements. So this is the number, the answer to the question that we are searching for. The second number indicates how many characters left of the input string remain to be matched. So this is the number of replacements, NR, and this is the index of the next token in the input string to match. And when the number of replacements is -1, that means there is no match. And before running this function, we have to compute a dictionary of the mapping tokens to all of the rules that exist for that token. So a rule is just a list of tokens. For example, this rule H goes to HO. Then we get the in the dictionary we have the list of tokens H and O. This encodes one rule for the H token. So in the parse function, the first argument is something called NT. This is from the parsing world, non-terminal. So this is essentially the NT is the token we want to match. S is the whole string that we are matching, and I is the position, the current position in the string which we need to match at. Fuel is the recursion limit. So when we run out of fuel, if fuel is 0, then we have to stop and we return no match. If I is past the end of the string, then we cannot match, so we return no match. Otherwise, we make a list. The list M contains all of the possible matches that we found, and we want to choose the best one. Then starting with the current token, if the current token is the same as the token we are trying to match, then that is one possible match, so we add it to the list. And this match is done with zero replacements, and it consumes one token from the input string, so we advance the index I by 1. And so this is an easy base case. Then we do a recursion here, where we need to try to match every possible rule for the current token NT. So we iterate over all the rules in the production dictionary for NT. So for one rule, for each rule we call the match function, which will try to match this rule R at position S, at position I in string S. And then we remove one fuel here because we are doing one recursion deeper. And then when we have enumerated all the possible answers that we can have in M, then we need to find the best answer. And I do this with the min function here. And if the M list was empty, it will result in no match here because we pass default equals no match. And the sorting order, the ordering here is important for when we choose the minimum. I want to choose the longest possible match, so I negate the second element of the tuple here for each element, and then we want to choose the lowest number of replacements in this order. So we value more that the match matches a longer part of the string, and then if this is equal, then we sort on the number of replacements, and we want to minimize that. So this is kind of a tricky way of doing this, using the key argument to min. It's useful for changing the sorting order used when finding the minimum. So if we have found best here that is not no match, then we want to check if the current token we are matching is the start token E. Then the length of the matched text must be equal to the string. We must match the entire string. Otherwise, the answer would be a partial match for the string. So a partial match, there are many possible partial matches, but we want to match the whole input string using the fewest number of replacements. If the token we are not matching currently is not the start token, then we don't care. We just return the best match. If this thing here doesn't hold true, then we just return no match. Okay, and then the helper function match here to match a rule at the current position I in the string s. Here we check if we are out of fuel. This is actually not necessary because we have checked this with the if statement above. Anyway, n is the number of replacements that we have performed, and we start with 1 because we are applying one rule here, this given rule. And then for every token in the rule in sequence, we try to parse this token, and if it fails, then we failed matching the whole rule. So then we return this empty list here, and this result is being concatenated up here to m, so returning empty here means we don't add a result. So ignore that part there, that was unnecessary. Anyway, if the thing here matched, then if it was not a no match, then we need to add the number of replacements to the running total, and then we have to update the position we are matching at. So if all the tokens did match, then we return the number of replacements that were performed and the following token to be matched. Okay, so that's how my solution works. My code didn't look exactly like this, but this is simplified. And my solution isn't completely sound, so using the min here does not work actually. And I won't explain why, but there are inputs that will fail on this, but it did work for my inputs. So my initial solution, what I just showed you, was too slow. And I thought about it a bit, and one optimization I could think about from an idea from the parsing world is to use the first set. So the first set of a token for a token t is all of the possible tokens that can be expanded from t to match, or well, t is a non-terminal, but it's any possible token that can occur as the first token when you apply any rule to t, and then recursively any other rule, continuing until you've explored all possibilities. So for example, if we have this rule h goes to ho, then initially we have the first set here, and we put the token itself into the set. So first is equal to h, and then we see what can we get if we expand h, and then we have also another rule here. These are the initial rules that we had in the problem description. Okay, so we could replace an h with OH. Now O is the first token in the result, so then we add O. Oh, and then imagine if we have another rule that O can be replaced by Rn. Then from the initial H we could get OH, and then by using the rule O equals Rn here, then we can get, using that rule, then we get RNH. So we got RNH from the initial H, so that means we have to add Rn into the first set, because now Rn is the first token. So if we do this, then we can realize that if we're trying to match a token to in a position in the string where none of the first tokens that we're trying to match exist at that position, then we can immediately reject the current token we are trying to parse. So I added that, and then my solution worked fast enough to complete in about a minute on the big problem input. But I don't think I used the intended solution for this problem. I was reading a bit about how others solve this problem, and there are some interesting patterns you can discover in the rules. So the fact that only that Rn, Y, and AR, these are separate tokens, they only occur in the right-hand side part of a rule. I noticed this when I was looking at the problem, but I didn't notice this fact that Rn is always before AR, and Y, if Y occurs in the right hand side, it's always between an Rn and an AR. So you can kind of think of these as Rn being equivalent to a left parenthesis and AR being equivalent to a right parenthesis. So these two should always match.